some more specific classes of learning algorithms and model classes such as support vector machines, logistic regressions, a little bit about neural nets, and a little bit about evaluation metrics. Just some announcements. Homework 1 is due tomorrow. Will be graded in about a week. I realize that there's still a few logistical things that the TAs are still working out, so please keep an eye out for some announcements on Piazza. We'll have more details about the grade scope submission later today. Homework 2 will be released tomorrow, possibly Thursday morning, but most likely tomorrow. It will be due the following Wednesday at 9 p.m., so the regular cadence for homework assignments will be due Wednesday at 9 p.m. There's a recitation this upcoming Thursday at 7:30 p.m. in Annenberg 105. For those of you who do not have as strong of a background in linear algebra and matrix variate calculus and vector calculus, this would be a nice recitation for you to get caught up in some of the basics in manipulating linear algebra and multivariable calculus. Any questions about the logistics? Okay, so just want to do a quick recap as before, just to keep building on the things that we've been seeing in class. So this is the basic recipe of supervised machine learning. We have a training set of XY pairs, where X is the input, typically expressed as a d-dimensional vector, and Y is a label, in this case a binary label, +1 or -1. That is the label that we are trying to predict given inputs X. And the goal is to first specify a model class, let's say a linear model class, although we've seen a few examples of quadratic and cubic, where it scores the input X as a function of the parameters of this linear model class W and V. We define a loss function that characterizes the mismatch between the ground truth, which is the first argument, and the prediction of our model, which is the second argument. And given all of these, we can put them into what's called a learning objective, which is basically the sum of the losses of between the ground truth yi and the model's prediction on input xi over all the xi and yi pairs in the training set. And our goal is to find the parameters of our function class that minimizes this loss function summed over the training set. And we saw in the previous lecture that one of the most common ways of doing this is variance of gradient descent, such as stochastic gradient descent. And that sort of gives you the entire recipe, at least at a high level, of how to do supervised machine learning, which is the most popular form of machine learning used in industry today and in many other applications, such as in science. We talked about the questions of overfitting. So even though you've set up a learning problem that can be solved using, let's say, the Python code that you guys wrote for homework 1, or more sophisticated software such as TensorFlow or PyTorch, even given all of that, how do you know whether your model is any good? And a lot of that comes to reasoning about the complexity of your model class, the representativeness of your training data, the size of your training data, the variability of how much your fitted model can vary based off different samples of the training data from the same distribution. And a lot of this is captured in a concept known as the bias variance trade-off, which is one of the central concepts to characterize overfitting. Where overfitting is the notion that your model has overfitted to idiosyncrasies of a small data sample of the whole distribution, and thus will not generalize to new data samples from that test distribution. And we saw this in play in a simple toy example of one-dimensional regression, where the x-axis here is a one-dimensional feature of going from 0 to 100, and the y-axis is the regression target. So this is a one-dimensional regression problem, which is also known as line fitting. And we compared linear, quadratic, and cubic model classes when trained on random samples of 7 data points from the test distribution, which are the red dots. And we see this nice bias variance trade-off, where some of the error comes from the fact that the model class itself is fundamentally unable to model the data well, and some of the error comes from the fact that with only 7 data points, there's a lot of variability in what the model can learn, also known as overfitting. And so here's sort of the complete pipeline. We have training data. We choose a set of model classes. Let's say, for the sake of argument, linear, quadratic, cubic. We have a loss function. We do what's called validation. In this particular case, cross-validation, to figure out which model class has the best test error. And we measure that by measuring the error of our trained model on a validation set. We pick the best model class, and this is all solved using stochastic gradient descent. And after that, we commit to a model class, we train a model, and we deploy that model. And that's, in a nutshell, what happens in practice. And certainly this is the pipeline that you should follow for the Kaggle competition mini project, which is mini project 1. Any questions? Okay. Today we will go into a little more details about specific classes of learning approaches that sort of take this generic flavor but go beyond, let's say, just using squared loss. And these will be the two big ones will be support vector machines and logistic regression. We'll talk a little bit about feed-forward neural networks. There will be an entire week devoted to deep learning in week 4. And so this will just be like a little teaser. And then we'll also talk about different ways of interpreting models and different other kinds of evaluation metrics that go beyond these simple instance level loss functions. Okay, so the two loss functions that we spent a lot of time talking about are 0-1 loss and squared loss. And one of the big challenges of 0-1 loss is that even though, in some sense, it is the loss function that corresponds to classification accuracy, right? So for classification accuracy, if the loss is 0 if it's classified accurately, which means the sign of the raw score function agrees with the sign of the label, and it's 1 if it's misclassified, which means the sign of the raw score function disagrees with the sign of the label. The problem with 0-1 loss is that if you actually plug that into the loss function for the optimization, you can't really solve it using gradient descent or variance of gradient descent, because the loss function is flat or discontinuous everywhere. It's discontinuous at the point where the raw score function is 0, because it just does a jump from loss of 1 to loss of 0, so it's not even continuous. And everywhere else is flat. So if my model is if my raw score function is making a prediction of -1, there's no information in the slope of this loss function that tells me which way to tweak or push the model's parameters to decrease the loss. I have no idea how to get to from a local view of over here, and remember this is all sitting in a very high dimensional space in practice. So from a local view of over here, I have no idea where the gradient doesn't have to tell me any information about how to push the score to over here. Whereas if you look at squared loss, which is the loss function of choice for regression, it gives the slope of the loss function gives a very clear signal as to what direction the gradient should go in order to improve the model with respect to measuring squared loss. So just to recap, 0-1 loss is flat or discontinuous everywhere, therefore it's very difficult to optimize using gradient descent. What people do in practice is choose a surrogate loss function that is easier to optimize and is hopefully optimizing this loss function will hopefully lead to good 0-1 loss. Now, if you look at this simple example, if I get perfect squared loss right here, or if my squared loss is pretty good, like in this region, then it implies that my 0-1 loss is pretty good. So squared loss, you can think of it as a surrogate for 0-1 loss. It's not the best surrogate. There are better ones, and we'll talk about two. The bulk of this lecture will be on two alternative loss functions that are surrogates for 0-1 loss. But squared loss is indeed a surrogate loss function for 0-1 loss. So let's talk about support vector machines, which are also known as max margin classifiers. So again, we're going to be talking about classification for the bulk of this lecture, and thinking through different ways of defining surrogate loss functions for 0-1 loss. So here is a separable classification problem, again in 2 dimensions, where we have 2 labels, the black labels and the white labels. One of them is positive, one of them is negative, doesn't matter which one. And between H1 and H2 and H3, it's clear that H1 is not a good classifier because it doesn't have 100% accuracy. It gets some of the examples wrong. H2 and H3, on the other hand, both correctly classify or separate the positive from the negative examples. Show of hands, just based on your intuition, which one of you think intuitively H2 is the better of the 2 classifiers? And which one of you thinks H3 is the better of the 2 classifiers? Okay, so most of you think H3 is the better of the 2 classifiers. Can anyone just give a sort of an intuitive explanation of why they think that is? Yes?
There's just more margin of error between each of the points.
Correct. There is more margin of error between each of the 2 points. You can imagine that if I had another training example, let's say a black training example, that just if I were to collect more data, and it was, let's say, over here, just as an intuitive argument, we'll make this a little bit more formal later, then H3 is still good, right? But on the other hand, H2 would have misclassified that example. Similarly, if I were to sample more data or to resample the training set, if I did a thought experiment where I resampled the training set, then I might get a white data example that's maybe like over here. Again, H3 is good. It would have gotten that accurately classified. H2 would have gotten that wrong. Okay, and so the margin is defined as the distance of the data point closest to the hyperplane. So the size of this gap is called the margin. So H3 has a much bigger margin than H2. We, of course, talked about this concept already when we talked about perceptrons. So there was a question, in fact, asked during the lecture on perceptrons as to whether or not we can explicitly solve for a classifier that achieves the maximum margin separating hyperplane. That was one of the questions asked during the lecture on perceptrons. And indeed, we're going to derive exactly that in the first half of this lecture. OK, so just a recap of some definitions. So we're going to talk about hyperplanes a lot in the first half of this lecture. You think of a line as a quote-unquote 1D plane, a plane, a colloquial, what we normally think of as a plane is a 2D plane. A hyperplane is just a plane in many dimensions. It includes line and planes as special cases, and is defined by a tangent vector and an offset. And geometrically, the tangent vector w, which is going to be the exact same w as in our linear model class definition, is the sort of the tangent vector that defines the hyperplane, and the offset is the offset from the origin. In the case where the w is normalized, so has norm 1, then the offset b is exactly the offset from the hyperplane, from the origin, excuse me. But in general, that's not the case. So you have to divide b by the norm of w. At least that's the geometric interpretation. The distance from a point to a hyperplane, is given by this formula. So you should have all learned this from your geometry class. We can also think of the signed distance, where we don't take the absolute value in the numerator. So now this gives us not only the distance from the point to the hyperplane, but which face is it on? Is it on the positive face or the negative face of the hyperplane? And a linear model from this geometric perspective simply gives you the score of the unnormalized signed distance of a point to the corresponding hyperplane in the geometric interpretation. Again, this is definition of the margin. So the margin of a So there's the margin achieved by a certain hyperplane, and there's the margin of separability of a certain learning problem. So here's a learning problem that's linearly separable. What is the achievable margin of this learning problem? And that's given by finding the W that achieves the largest margin. And that's given by this pictorial depiction here. And so the goal then is to find this W and B, but I'm not talking about B in this particular example, just for simplicity. Okay. So this is going to be the question that we're going to look at for a little while. How do we maximize the margin? And to begin with, we're going to assume that the data is linearly separable. I'll show you how to extend support vector machines to, or what will become support vector machines, to the case where the data is not linearly separable after we look at the separable case. So it's quite simple. We choose the W and the B, and sometimes I'm not going to talk about B just to keep it simple. The math just gets a lot more complicated. The intuition stays exactly the same. that has the highest margin. The margin of for any given WB is simply the XY pair, the positive and negative pair that has the minimum distance. And remember that since we're looking at sign distance, we care about, so if this is a negative example, we care about the one that has the smallest negative sign distance. If it's a positive example, we care about the one that has the smallest positive sign distance. So that's why we multiply by y, so that everything is positive. And again, this is only looking at, I should also mention, this is only looking at data points that, hyperplanes that separate the data. So these are only looking at hyperplanes that achieve 100% training accuracy. Because right now, we're assuming that the data is linearly separable. Any questions so far? Yes?
So instead of multiplying the sign distance by y, why not just look at the sign distance?
So first of all, at this level of simplicity, they're essentially mathematically equivalent. The reason why we're going to do that will become apparent as we extend to the case where it's not linearly separable. This will be a more convenient starting point to when it's not linearly separable. Okay. So there's some interesting aspects of this problem, of this particular optimization problem. So first of all, there's an infinite number of solutions. I can multiply W and B by a factor of 10, and I get the exact same solution. I can multiply W and B by a factor of 0.000001, and I get the exact same solution. So there's like this subspace of infinite of equivalent solutions, because I'm multiplying. Ignore B for now. I can multiply W by 10, and I divide by the new denominator also increases by a factor of 10. So they're all equivalent. So we want to find one solution. And since they're all equivalent, one option is, let's just hold the denominator fixed. Let's assume the denominator is 1 without loss of generality, which means find the W and B such that the norm of W equals 1. This is an equivalent optimization problem. They yield an equivalent solution up to a scale invariant. There's an alternative, so that in the end will lead to a more elegant extension to the non-linearly separable case, and that's if we hold the numerator fixed. Because we can hold either the denominator or numerator fixed. The problem is that they both scale up or down, right? So let's just hold the numerator fixed. Let's force the unnormalized sign distance multiplied by y to be equal to 1. In which case, to minimize this, sorry, that should be divide by W, sorry. In which case, to minimize this, we simply, sorry, this is actually what I meant. Then if we force the numerator to be equal to 1, then this minimization problem, this max-min problem, simply becomes finding the W and the B that has minimum norm, such that its minimum, its margin is 1. Its unnormalized margin is exactly 1. For convenience, we often square it. If we find the W with minimum squared norm, again, squaring is a monotonic function, so it doesn't change the solution. So the solution to argument of W squared is equal to the argument of W, such that the W has this property. So here's another way of writing it that's mathematically equivalent. And we're going to walk through this formulation very carefully.
Could you go back one
Yeah.
real quick? So you're saying that argmax WB of the minimization of XW of 1
Yeah, we're trying to. So let's say that we. Let's say we force the numerator to be 1. In which case, this minimization x comma y doesn't affect the denominator at all. The only thing we care about are the set of w's. The only thing we care about here, if we force the numerator to be 1, the only thing we care about is the set of w's. So I perhaps should have used more notation here. The set of, and that's, and I sort of, I'm a bit informal here. It's going to be more formal in the next slide. But I'm going to choose, I want to look over the set of w's such that the numerator equals 1, because I force the numerator to be 1. But then I want to maximize this inner term. And if the numerator is forced to be 1, then the maximum of this is the minimum of this. There's a good reason why we do this. It'll become evident in a few more slides. But I guess in this particular slide, the point is, if we start with this as the optimization problem, which is the natural optimization problem to think about when you think about finding the maximum margins hyperplane, the first observation, just to recap everything I said in the last 5 minutes, the first observation is that there's an infinite number of solutions because you can scale both the numerator and the denominator up and down, and it's the same exact answer up to scaling. What people often do, at least people's first instinct, is to fix the denominator of this interior term, in which case you get this particular optimization problem. For reasons that will become clear in the next few slides, if we want to have a formulation that is easily extendable to the non-linearly separable case, it makes more sense to hold the numerator fixed. And without loss of generality, let's force the numerator to be 1, which means we're only interested in w's where the minimum x comma y of y times w transpose x minus b equals 1. So this term has to be 1. Notice that this min only needs to be in the numerator, and perhaps this is something that I should make clear later. This min only needs to be in the numerator, not the denominator, because the denominator is independent of the specific xy pair. And so I only care about the w's that satisfies that the numerator equals 1, that has such that 1 over the norm of w is maximized, which means the norm of w is minimized. And it'll be mathematically convenient to consider the min norm of w squared, which, since the square function is monotonic, this doesn't change the optimal solution. It has the equivalent optimal solution. Yes?
When you enforce this numerator equals to 1, is it kind of like making a change of basis to where that vector x for which that is true is like a new unit basis vector for you in some sense?
Yes, actually. So the question is, okay. So yeah, the answer is yes, and the full explanation is beyond the scope of this class. And the answer is, do the specific choice of x has some interpretation as a basis function? And the answer is yes. If you're interested in full details, we can talk during my office hours. It's the full explanation is beyond what I'm willing to spend during class.
Okay.
Yeah. Nor is it on the homework, which is what I think most people hear about. So here is, I'm just going to rewrite the optimization problem again, starting from this interpretation, forcing the numerator to be 1, and then rather than maximizing 1 over the norm of w, we minimize the norm of w squared, because the squaring doesn't change the solution. And it gives you this. We minimize the squared norm of w. I'm dividing by half for, again, mathematical convenience, because when you take the gradients and stuff, you have a 2 because of chain rule and stuff. And anyways, and then this constraint. So this is what's called a constrained optimization problem. We want to find a w and b that has minimum, in this particular case, 1/2 squared norm of w, such that for all data points in my training set, for all I, y sub I times the raw score, W transpose X of I minus B is greater than or equal to 1. Okay. And then now you can verify for yourself that this is essentially equivalent to the starting optimization problem that we started with. That was sort of the mathematical embodiment of the intuition, find the maximum margin hyperplane. We did a number of mathematical transformations of that optimization problem to arrive at this one. And what I mean by equivalent is simply that the solution of this optimization problem is the solution to the original optimization problem. That's what it means for two optimization problems to be equivalent. And we can verify this. So suppose that there exists some suppose that for all I there exists a W. Sorry. Let me back up. I tied my tongue. So the first thing we want to check is that the numerator is satisfied, which means that the minimizer, the min xy of this term is 1. And so here's how we can check that this is true. Suppose that it's not true. So we're going to do a proof by contradiction. Suppose that it's not true. And suppose that there exists, suppose that the minimum is, let's say, 1, let's say it's 2 without loss of generality, some constant that's greater than 1. Let's say it's 2. That means that, for all I, for all data points, this quantity is at least 2, right? So here's what we can do. We can divide W and B by 2, okay? And in fact, if you divide W and B by 2, it still satisfies these constraints. So it's still a satisfactory solution point in the optimization problem, and we've reduced the objective function. We've reduced the objective function by a factor of 2, which means the original solution wasn't actually the solution of this problem. So that's a contradiction. And in fact, you can see, and therefore, the solution of this problem must satisfy that the minimal xy pair must satisfy this equals to 1. So the margin that we force the unnormalized margin to be exactly 1. And so therefore you can see that this particular optimization problem is equivalent to this particular optimization problem where because there's infinite number of solutions, we force the numerator to be 1. Okay, so here's sort of a geometric depiction of the problem. So let's look at the actual figure. We have this W. Let's say this is the solution of this optimization problem. Recall that you can check that the distance between these two is 2 over the normal of W, and 1 over the normal of W is actually the margin. You can check, and these are the points that satisfy that W transpose X minus B equals 1 or minus 1, because these are the negative points. This is the support vector machine. This is exactly the formulation that is used to find the max margin separating hyperplane of a linearly separable supervised learning problem. Any questions? Okay, so there's some interesting properties of this solution when you look at the geometric interpretation of this, what's happening, right? So what happens if I remove this data point from the training set? What happens to the learning problem? Any takers? Yes.
Stays the same.
It stays the same. What happens if I remove this data point from the training set? Same thing. The solution stays the same. The only time that the solution changes at all is if one of these 3 points is removed, or some other point gets added that is closer to W, to the hyperplane, than one of these 3 points. In all other cases, the solution stays exactly the same. And these 3 points are called the support vectors of the solution. And if you're interested in sort of functional analysis, this can be extended beyond the linear space in Euclidean space to a general, what's called a Hilbert space, in which case the 3 points have a basis interpretation. Okay, so this is for the linearly separable case. In general, data points are learning problems are not linearly separable, but it's important to start with the linearly separable case just to work out the math in a very mathematically clean formulation. As you can see, this optimization problem is a relatively easy optimization problem to solve. And the reason why we do this, which was a question that was raised earlier, is that this particular formulation has a nice extension to the non-linearly separable case. Okay, so let's look at the non-linearly separable case. I just added 2 data points to make this problem not linearly separable. These 2 data points. So now this particular solution, has 2 data points that sit in between this margin that we computed. And we call this a margin violation. So here's how we handle the non-linearly separable case. We have this thing. It's called the slack variable. And so what happens is we want to find the W that has minimum 2 norm plus has minimal slacks or margin violations. So what does that mean? That means that, let's say for this data point, because yi, for this data point, yi times wxi minus b is less than 1, right? So it's about 0.2, let's say. Then the slack variable, in order for this constraint to be satisfied, the slack variable has to be, let's say, 0.8, which means we pay a penalty of 0.8 in the objective function. This data point, the margin is violated by, let's say, it's 1.5, because it's supposed to be on this side of this. It's supposed to be over here. And so in order for this optimization problem to be, for this constraint to be satisfied, we must set this slack variable to 1.5. So we pay a penalty of 1.5. And so now we're trying to find the hyperplane that that separates most of the data points with as big a margin as possible. Remember, the margin is 1 over the norm of W. So minimizing the norm of W maximizes the margin, right? So we're trying to find the W that maximizes the margin of as many data points as possible while tolerating just a little bit of margin violation from a subset of the data points. That's the interpretation of this learning objective. So this is called the soft margin support vector machine. In the linearly separable case, it's nowadays known as the hard margin support vector machine. Historically, it was just called the support vector machine. But once you talk about data that's not linearly separable, there's the distinction between hard margin and soft margin. So this particular learning objective controls a trade-off. So C, capital C, is a tuning parameter or a hyperparameter of the learning objective, which says how much do I care about maximizing the margin versus minimizing the number of violations. So, I can choose a different hyperplane, let's say one that cuts through here, that where the margin of violation is really small, but then the margin's also really small. So how do I care about that trade-off? Okay, so in the first 2 lectures, we talked about our learning objective as having a loss function. And now let's try to interpret what's happening here as a loss function. And in particular, I'll show you that the support vector machine learning approach is equivalent to minimizing what's called the hinge loss. What is the hinge loss? The hinge loss is defined as follows. So here's our loss function. We have the ground truth label. It's either +1 or -1. So we're again just sticking with binary classification right now. And then we have the raw score. So we don't take the sign right now, just the raw score of the model on a data point. The hinge loss is defined as follows. It's the max operator over 0 or 1 minus yi times f of xi. So what does this mean? This means that if yi is +1, let's say right here, yi is +1, then if xi is at least +1, then 1 minus yi f of xi is going to be negative. And since we floor it at 0, then everything over here for the prediction of f of x, the loss will be 0. Whenever the prediction of f of x is less than +1, in the case where yi is +1, then we get this linearly increasing loss as a function of how far the score f of xi is from +1. And then the same is true if yi is -1. So this is the shape of the hinge loss, this green line. And just to compare it with the shape of 0, 1 loss. And now you can see that the hinge loss is indeed a loss function that we know how to optimize. And it's also one that seems like a reasonable surrogate to 0, 1 loss. And in many cases, it's a much better surrogate to 0, 1 loss than squared loss. Now, something that we'll talk about more in lecture 4, which I won't really talk about in this lecture, is this interpretation of this first term, the 1/2 times the square norm of w. So I basically told you that this slack variable, which is equivalent to this formula. So you can check that the slack variable under this optimization problem is equivalent to this formula. I basically told you that the slack variable is exactly the hinge loss, but this particular learning objective is minimizing the sum of this norm of w squared times 1/2 plus the hinge loss, sum of hinge loss over the training examples. So what is this norm of w squared? It's this thing we call regularization. I gave you a particular geometric interpretation of it for support vector machines, but in general, there's for general loss functions, it has a more general meaning. And we'll talk about this more general meaning in lecture 4 on Thursday. For now, are there any questions? Okay, so this is just a comparison of 0, 1 loss versus hinge loss versus squared loss. You can see that hinge loss, when the model is making an error, it has this non-zero slope that encourages the model score to get closer and closer to the target. It has the loss function becomes flat after you exceed the margin, right? You can see the geometric interpretation of the margin embedded in the shape of this loss function. because if you're beyond the margin, then the loss function is completely, oblivious to that data point. And the data point only contributes. A signal to the training loss if it's at the margin or within the margin. So you can actually see the geometric interpretation embedded in the shape of this training function, in the shape of this loss function. Yes?
And how do you deal with it at 1 because it's not fully continuous?
Right, so the question, how do you deal with at 1 because it's not fully continuous? So it is continuous. The gradient is not well defined, but it is continuous. So 0, 1 loss is actually discontinuous. There's I couldn't plot this in a plot, but because I was lazy, but so I didn't want to plot two separate lines. But this line doesn't exist, right? This is truly discontinuous. Whereas hinge loss is actually continuous. It's just that the gradient is not uniquely defined at a specific point. We're going to talk about that in lecture 4. But that's different from it being discontinuous. Okay, so let's go back to the perceptual learning algorithm. So I'm going to go through this pretty quickly. It goes through the training examples. It has this update rule where if the sign of the prediction agrees, then we don't make an update. Otherwise, we'll make an update like this, right? So this is something that we talked about very briefly. And we talked about, more importantly, we talked about this loss function. The loss function of the perceptron, the loss function that the perceptron is implicitly optimizing by definition of its algorithm is the following loss function. And the hinge loss that the SVM is optimizing looks like this. And the biggest difference is that this loss function that the perceptron is implicitly optimizing, it's the signal from the loss function disappears as soon as you correctly classify this particular training example. Whereas for SVMs, the training signal only disappears after you correctly classify this training example to at least a margin. And so this very subtle difference leads to a very different sort of properties in terms of whether or not you're able to find the max margin classifier. Obviously, the perception algorithm predates the SVM by around 30 years. So but it's important to see this difference. Okay, so just to summarize, in the first half of this lecture, we saw the support vector machine. And the support vector machine is specified by this particular learning objective. We also saw two interpretations of the support vector machine. The first one is geometric, right? So we are trying to maximize the margin, hyperplane that has maximum margin between most of the training positive examples and most of the negative examples, and balance that against the size of the margin violations. The second interpretation, which is the canonical interpretation we take in this class, although I suppose it doesn't need to be the canonical interpretation in general, but it is the canonical interpretation we take in this class, which is we're trying to specify a loss function and we're trying to minimize it. So that's the second interpretation, and that's the default interpretation we do take in this class. And it's a trade-off. This objective function is a trade-off between a measure of model complexity, which again we'll talk about in more depth in lecture 4, and a loss function, which is the hinge loss. So it's not 0, 1 loss, it's not squared loss, it's this new loss function that we just saw called hinge loss. And so that is the support vector machine. And indeed, these two interpretations are mathematically equivalent. Each one implies the other one. There's a bijection between the two. And that is something you'll see come up time and again in many of these methods, where you can derive the exact same algorithm or learning approach from a different perspective. And it turns out that these perspectives there's a tight connection between them. Sometimes they're not exactly equivalent, but oftentimes, at least for the simple cases, they are exactly equivalent. In fact, one of the big hot topics in research in machine learning right now is finding all these different interpretations of what's going on in deep learning, and finding the connections between these different interpretations, geometric versus statistical mechanics versus otherwise. So if you're interested in that, that's a topic of contemporary research in the community right now, because we don't actually understand what's going on. Okay, so just a comment on optimization. So this is something that was brought up just a few minutes ago. The hinge loss is not smooth. It's continuous, but it's not smooth, which means the gradient is not well defined everywhere. In particular, it's not defined at this hinge. That's why it's called hinge loss, by the way. There's this hinge right here. So we're going to talk about this in the next lecture, but what you can still use stochastic gradient descent. You just can't use the exact gradient, but there's a more general concept called the subgradient. When the function is differentiable, the subgradient is unique. When the function is not differentiable but still convex, which it is, with the hinge loss is still convex, the subgradient is a set. There's a set of subgradients that you can, and we'll talk about more of this in the next lecture. Any questions about support vector machines? Okay, the second big topic we're going to talk about today is logistic regression, also sometimes referred to as log linear models. So this might be one of the first approaches people learn in their statistics class, data science class. It's one of the first methods that people learn, and there are many different equivalent formulations if you manipulate the algebra. I just wrote one up here. And it's basically, so you have this linear, so in the simplest case for a linear logistic regression, you have this linear scoring function that you exponentiate, and then you sort of, and there's, again, many different formulations. There's this formulation, there's this formulation. Yeah, so here's a different way of writing it. They're mathematical equivalent, and people often interpret this value, because it's bounded between 0 and 1, as a probability or a conditional probability. So what is the probability that the label is y, given input x and given parameters the model w comma b, and it takes this shape. So as y times f of x gets really large, the probability becomes close to 1. As y times f of x becomes a very big negative number, the probability gets close to 0. And this y times f of x is inside this exponential term here. By the way, this function is also known as a sigmoid. Okay. So how do we train a logistic regression model? I'm going to start with a probabilistic interpretation. We have a training set of xy pairs. And our goal is to maximize the likelihood of the labels in our xy pairs given the model, and we're going to maximize the likelihood as the product of the likelihoods of the individual xy pairs. Can anyone tell me why we maximize the product of the probabilities of the data points? Yes?
If you predict something has a probability of 0, then that's like the worst thing, so you should be penalized at negative infinity.
I'm trying to understand your answer.
Predict something has a probability of 0 and it happens, you should be like really penalized for that.
But that requires w to be that requires the score. So in order for the probability to be 0, to be actually 0, I mean, of course there's numerical underflow and stuff like that, but ignoring underflow, in order for the probability to be exactly 0, then this score has to be exactly negative infinity. So that's not quite the answer I'm looking for. Yes?
You assume they're IID?
Okay, yes, IID. So IID, for those of you who don't remember, it stands for identically and independently distributed, which means each data point, xy pair, is sampled independently from the training set. And because they're sampled independently, if I want to maximize the probability, the joint probability of predicting yi given xi, because they're independent, they factorize into the probability, into the individual probabilities of yi given each individual xi. And this is a standard assumption people make in probabilistic modeling. And so when they try to maximize the probability of some data instance, that probability of a data set, when they're trying to maximize the probability of a data set in terms of maximum likelihood, they typically factorize that multiplicatively across the individual data points. If you're, this type of manipulation and reasoning about probability will be discussed further in the probability recitation, which will happen in a few weeks when we talk about probabilistic models. But I just wanted to briefly touch on it here. Why might we want to use logistic regression? There's a few reasons why one might want to do that. SVMs are often better at classification, assuming a margin exists. But let's say you wanted to predict calibrated probabilities. So you have a messy data set where the data is not cleanly separated, and you have this you have regions of the input space of x's where it's like 80% ones and 20% minus ones, and other regions where it's like 60% ones and 40% minus ones. You want to actually be able to predict these calibrated probabilities. So logistic regression is one way to be able to train a model to encourage it to actually predict these calibrated probabilities in cases where the data is clearly not linearly separable. So SVMs are known to be not well calibrated for these things. Like the hinge loss margin violation measurement is known to not be well calibrated with the probability of a label being plus or minus 1 in a certain region of the input space. And that's why we use logistic regression. Okay, so now let's talk about a loss function. And in particular, the loss function is commonly referred to as log loss. So we start with the maximum likelihood objective. And all I'm going to do is take the negative log of the maximum likelihood objective. I'm going to take the negative log of it, which turns the negative log is a strict monotonic function. So again, it doesn't change the optimal solution because it's a strict monotonic function. So I take the negative log of this whole thing. And so what was a maximization problem, because I take the negative of it, becomes a minimization problem because I'm doing a negation operator. And then the log of a product is the sum of the log. And this is called log loss, right? So now this looks a lot like a loss function that we would use in our recipe that we discussed in the opening lectures. But now this loss function looks like this. So it looks like yi is the input, and then f of x looks like this. And we take the negative log of this formula. So this is another loss function. It's called log loss. This, in fact, is the most popular loss function used today. This is the default loss function used to train deep neural nets for many applications. Now I'm going to give you sort of this, again, I'm going to give you this sort of comparison of the shapes of the loss functions. Again, remember that scale doesn't really matter. Like I can multiply like a loss function by like a factor of 5. The scale doesn't really matter. It's only the shape of the loss function that matters. So the fact that this purple line, doesn't completely cover this blue line, that doesn't actually mean anything, because I can just multiply this purple line, the log loss, by a factor of like, looks like a 1.3, by a factor about 1.3, and it doesn't change the shape of it doesn't change the minimal solution at all. So the scale doesn't matter, it's only the shape that matters. So what are some nice properties of log loss, or what are some interesting properties of log loss? Well, when the model score, again, the target label is +1. I forgot to annotate that here. The target label is +1. So for this simple example, the ground truth label is +1 for this example. So as the model score starts to strongly disagree with the target label, for hinge loss, you get this straight line loss that increases linearly as the disagreement increases. For log loss, actually, it asymptotically converges to a linear function as well. So in the asymptotic limit, log loss and hinge loss both have this a linear increase in loss. Squared loss has a quadratic increase in loss. Log loss and hinge loss all have a linear increase in loss in the asymptotic extreme of large disagreement. In the asymptotic regime of large agreement, where the raw score is very positive and the label is +1, then both log loss and hinge loss becomes flat. The difference is this intermediate region, where hinge loss is linear until you cross a margin of 1 and it's immediately flat, whereas log loss has this more gradual transition from linear to flat, if you actually look at the shape of the loss functions in this plot. So they're very closely related. It's just that they have a very different, they have a very different behavior in this intermediate region. Why might this matter? If you're not able to perfectly classify every example, your loss function is going to be your learning objective is going to have to make trade-offs, right? Because if you try to minimize the sum over these guys, how you penalize these different loss functions penalize or degrees of disagreement differently, and so you're going to have to make trade-offs into which data points you have a stronger gradient or a stronger signal that contributes to what W and B you learn. And looking at the differences in shape of the loss functions help you understand what kind of trade-offs these different loss functions are making. Yes?
So with log loss, if the label is +1 is correct, is this showing you still have some loss value even if you are labeling completely correctly?
Yes, that's right. So if you think about the probabilistic interpretation of this loss function, it's basically saying because I put the score function inside the sigmoid, the probability that for me to be 100% confident that the label is y, this score needs to be positive infinity. Yeah. So as long as that score is not positive infinity, I'm going to incur some very small loss. Of course, that loss quickly converges to what looks like a flat function very quickly. So even here, it pretty much looks like a flat function. I mean, the slope here is the slope here is basically 0, right? Like for all practical purposes, looks like this is infinity. Yeah. Yes?
Is this like the same thing as binary cross entropy?
Yes. Yes.
Why is that? Sorry. Like can you maybe talk a little bit about what binary cross, why is it called that?
So in deep learning was popularized. So the question is this equivalent to binary cross entropy? The answer is yes. The exact mathematical formula might be a little bit different, but they're effectively equivalent, if not exactly equivalent. I think they're exactly equivalent. The reason why it's called binary cross entropy is for some curious historical reasons. And perhaps I'll add a modification to the slide that says equivalent to binary cross entropy. In deep learning, in 2012, it was popularized, between 2012 and 2014, deep learning became extremely popular because it won this competition on a dataset called ImageNet. And ImageNet had 1,000 categories. So there's an extension of log loss to multi-class classification rather than binary classification, and they called that the they called that the cross entropy loss. It's just an extension of log loss. The log loss definition comes from the people who take this log probability perspective, this more probabilistic perspective of deriving this loss function. So it's just a different naming convention. And so yes, log loss, as I presented here, is basically binary cross entropy. Yes?
Out of curiosity, can you make something akin to log loss by like playing with the weights associated with hinge loss?
Yes. So there is a paper that shows that there's an entire family of loss functions that interpolates between log loss and hinge loss. Yeah. That is beyond the scope of this class and will not be on the homework. Yeah. Okay. Just a quick run through of how one might derive the gradient. Again, I expect all of you guys to be able to do this yourselves, but maybe just to see just a working example. Again, I'm just only going to look at a single example here because of linearity of the differentiation. This is the probability term down here, definition of the probabilistic interpretation. And so you apply the gradient on both the numerator and denominator. You get something that looks like this. And then this is since this f is linear, you get something that looks like this. And then you distribute the gradient operator to these two additive terms. The first one is easy. The second one, you have to go through another log, and then you get something. Again, you don't have to go through you don't have to follow all the details. You can derive this yourselves in your spare time. But you get something that looks like this. So what does that look? What does that mean? So now we can actually give an interpretation of this, right? So the gradient of a specific data point, on the loss, if you're doing gradient descent or stochastic gradient descent, has this interpretation. How far is my confidence from what I want it to be? So if the label, if the ground truth is, if my prediction, my conditional probability of yi is 70%, 0.7, then I'm 0.3 away from being 100% confident. So I'm doing this linear update, because it's a linear model, in the direction of the positive or negative label. And the magnitude is weighted by how confident I am. If I'm not confident at all, like if I'm completely wrong, like I think the probability is almost 0, then this weight is very big. If I'm almost sure, like the scoring function is such that this conditional probability is like 0.99, then that is a very small weight. And this is actually just a straight up, standard, derivation using multivariable calculus. So the gradient update has this nice interpretation. Okay, so just to summarize for a logistic regression, we again saw two interpretations. The first is maximizing log likelihood of this conditional probability model. The second one is I have this new loss function called log loss, also these days often referred to as binary cross entropy. And again, they are equivalent. So in this class, we do take the default position that we're going to derive learning approaches based from a perspective of loss functions, but you should just keep in mind that there are multiple equivalent perspectives from which one can derive learning algorithms. Any questions? Okay, so for the remainder of the class, or about 15 minutes or 10 to 15 minutes or so, I'm just going to survey through a few topics. The first one is feed-forward neural nets. So this is sort of just like a precursor to week 4. In week 4, we're going to talk about deep learning in depth, pun intended, I guess. But today I'm just going to do a quick teaser just to explain the relationships. A one-layer neural network. So in deep learning terminology, we call this like a neuron. sort of inspired by neuroscience. This is like, you could think of this as an artificial neuron, which takes as input. It's typically it's often described in this type of diagram where each circle here is a feature. So this is a three-dimensional feature vector. There's an aggregator, there's a weighted aggregator, that's your linear dot product, and then there's a nonlinear transform that gets your output y. So, this is basically the aggregator. And then let's say we use a sigmoid function for the f of for this nonlinearity, and we get y. So there are many nonlinearities we can use. We can use ReLUs, we can use rectilinears, we can use sigmoids, hypertangents. This is actually logistic regression, right? So a degenerate one single neuron, one layer neural net is actually, with a sigmoid nonlinearity, is just logistic regression that we just saw. Okay, let's do a two-layer neural network. So the first layer takes as input the raw features. So in this case, a three-dimensional feature vector. We have two logistic regression models. Let's say the nonlinearities are all sigmoids. We'll talk about other nonlinearities such as ReLUs in week 4 in much greater detail. But let's say we have two logistic regression models here. Those are the two individual neurons. And their outputs are actually the inputs to another neuron, which is the second layer. So now this is a two-layer neural network. And now this is the final output y. So it's a logistic regression on the outputs of two different logistic regression models in this particular simple example. This is actually a nonlinear function class. So all the function classes we talked about before were linear functions with maybe one monotonically nonlinear transform, but essentially still a linear function. This is a very explicitly a nonlinear function class. And indeed, this particular construction, assuming that you can have many different neurons in this in this first layer, also known as a hidden layer, can approximate arbitrary functions. So a deep neural network is simply a composition of this form that has many layers. These days you can have, I think in the record is about 10,000 layers. But in practice, typically you can go up to hundreds of layers. There are many reasons why people prefer these fat layers over deep layers over fat, shallow layers. It tends to be a more compact model. There's some evidence that suggests that it's easier to train, and this will be discussed further in the deep learning lectures. So that's all I'm going to say. I think I'm going to skip the gradient descent derivation. It's just an absurd amount of chain rules. So the story so far, different loss functions that can be derived from different interpretations, the T0 nonlinear model classes. Starting week 3, we're going to only talk about nonlinear model classes for a long time. And must use gradient descent for training. So the final 8 or 9 minutes, we're going to talk about just a few other ways of evaluating the performance of your model. So we have 0-1 loss, we have squared loss, we have surrogates of 0-1 loss. What else is there? So let me give you an example in cancer prediction. So I'm going to do what's called a confusion matrix or a confusion table. So we have the prediction of their model, has cancer or no cancer, and then we have the ground truth, has cancer or no cancer. So if we predict has cancer, and the patient truly has cancer, let's say the loss is low, intuitively. If we predict the patient has cancer and the patient doesn't have cancer, let's say the loss function is medium. We can actually debate this, but let's just say the loss function is medium, intuitively. If we predict no cancer and the patient actually has cancer, the loss function is huge, intuitively, right? The loss should be huge. And then if we predict no cancer and the patient doesn't have cancer, the loss function is again low. Okay. So what's an interesting property of this of this thought experiment? Well, we actually value positives and negatives differently. All the loss functions before, it doesn't care if yi was +1 or -1. It treated it symmetrically. Here, we're not. We care much more about the positives. So 0, 1 loss is a special case where this matrix is, I guess because of the way I wrote it, is anti-symmetric. But you know, it must not have the symmetry for these kind of where if you treat positive and negative cases asymmetrically. So the simplest approach, and one that people often use, may or may not be the best, depending on the application, is to just weight the loss function for the negative examples or one of the labels much more than the other one. So if you mispredict on the positive labels, you pay 1,000 times higher loss than if you mispredict on the negative labels. Simple thing, just keep that in mind. Here's a few other concepts. They're called precision and recall. So oftentimes we use our model to make predictions for some downstream task. Let's say we're prioritizing, this is something that's very common these days in the discourse about machine learning for medical decision making. Let's say we're trying to figure out who to prioritize for doing a biopsy. Right? Biopsy is where they actually extract a piece of tissue from your body and then do a further test to determine whether it's cancerous or not. So based on an X-ray scan, we're going to prioritize who to do a biopsy first. Biopsies take time, they take resources, so you have to rank who to do a biopsy with first, or who not to do a biopsy with because the risk is low enough. And so to think about these things, we have to think about the concepts such as true positive, true negative, false positive, and false negative. So true positive is your model the truth is it's actually cancer, so true positive, and we predict cancer. False positive means we predict cancer, but it's not actually cancer. We predict positive, but it's false. False negative is where we predict false, doesn't have cancer, but that's actually wrong. It's actually the person actually has cancer. And then true negatives. So two commonly used metrics that people use to evaluate how good your model is, especially if your model is being used for downstream decision making, are precision and recall. So precision is true positives divided by true positives plus false positives. So this number divided by the sum of this row. So in this case, it's 20 over 50, or 40%. So of the ones that you predicted positive, what fraction are actually positive? Recall is true positive divided by true positive plus false negative. So this number divided by this column. So 20 over 25, or 80%. Of the ones who actually have cancer, how many did you predict have cancer? Both of these metrics ignore the bottom right cell, which is true negative. So they are asymmetric measures of how well you're doing. They don't treat positive and negatives equally. And there's that b hyperparameter, the threshold function. You can increase or decrease that b to vary what becomes positive or negative. And when people do these type of analysis, they train their model and they just slide their b up and down. And so if you increase your b higher, the threshold for predicting positive is higher. If you slide your b down, the threshold for predicting positive is lower. And so you can get these precision recall curves. Okay, suppose we're doing ranking. Suppose we're doing explicit ranking. We're going to take all the X-ray images. We're going to rank them by most risky to least risky, or search engines. Rank by most relevant versus least relevant. I'm going to skip this particular example and just talk about this guy. So one way to think about how to measure the quality of an entire ranking over a data set is to compute ranking measures. And one ranking measure is based on pairwise disagreements. So if we rank along this axis, so this is the top ranked item, and this is actually not a negative item, so maybe in the case of cancer, not cancer, then this particular case has two pairwise disagreements. This pair is misranked. and this pair is misranked. And for pairwise agreements, these pairs are all correctly ranked. And that's what is essentially the most commonly used ranking measure in practice, which is called the ROC area, which measures the fraction of the rankings, of the pairwise agreements. I'm running a little short on time, so I'm skipping through this. But if you're interested, you can, of course, look at the slides more carefully. So I'll skip this guy. The last thing I want to talk about are other challenges. So these, so far, we've talked largely about regression and binary classification. But in a much more structured prediction task, which often arise in computer vision, let's say, things get really complicated. So here, I want to predict bounding boxes of vehicles. This is a very, very important problem. Let's say if you're building the system for a self-driving car, right? I want to predict bounding boxes over vehicles. Now, this is not really classification or regression anymore. And in fact, measuring how well you're doing is extremely challenging, or at least non-trivial, right? So for example, you know, there's the ground truth bounding box. This red, the red is the ground truth bounding box, and then the green is the prediction. And there's, you know, it's actually a little bit off. It's not exactly correct. But do we flag that as correct or not? Here's a different one where, you know, if we make this as the bounding box, that's an error because it, you know, somehow there's two reasons why it's an error. First reason is it only got half the car. Let's say that's an error, although it's a judgment call. It depends on your application if that's an error or not. The second thing is that I actually gave two bounding boxes that overlapped with each other. We gave two bounding boxes that overlapped on the same car. Is that an error? No. So these get really complicated. So whenever you have these sort of kind of these segmentation or localization problems in spatial temporal data, such as bounding boxes around some kind of activity, you know, this gets very complicated. Let's say we're doing health monitoring, and we're monitoring someone's heart rate, and we say we want to say that this person had a heart attack. Well, what does that even mean? How do you label that? And if there's like a region of time where that heart attack or irregular heart behavior was happening, like how do you bound that in time? Do you underbound it? Do you overbound it? Do you segment it into multiple ones if there's only one? These are all complicated questions that arise when you get into truly real-world problems in machine learning. So, of course, that's beyond the scope of this particular class, but I'm happy to talk about that during my office hours if you're interested in learning more. So just to summarize, you know, in the real world, evaluating how well your machine learning model is doing is very dependent on the downstream use case that you use machine learning for. And that leads to different evaluation measures that try to characterize different downstream usage scenarios. In the next lecture, we'll talk about regularization and lasso. And on Thursday, we have a recitation on matrix linear algebra. That's it.